Hi again, everybody. Welcome back to Orgoland. Where are we going today? What scary place are we happening? I got this for you. Okay. So enough of that. Really, I'm just having fun with this idea of eliminations and how many ways can we be scared and eliminated. And yes, that's me pre-mustache. Yeah, and me and Arnold we're really tight. We're close. So let's go play again and learn a few different ways of making alkenes and some rules about making alkenes. There's Zaitsev's rule and Hofmann's rule, and they will play a role in what kind of alkenes we can make. We know how to make them, but what kind of alkenes? We'll see what that means in a second. And then we'll dabble in E1. Okay. There's also a little part that I can't wait to show you in 11.12 that it relates to alkenes. So I thought I'd bring it out of chapter 11 and throw it in here because it's so closely related to alkenes. All right, let's go play. Zaitsev's rule. Zaitsev rocks. This Russian had a great idea. He was able to study the formation of alkenes. And again, I just labeled this with all sorts of different colors for you. And I just still want you to classify this as an E2 reaction because the leaving group is on a secondary aliphatic carbon. So even though that's a strong nucleophile, it will only react SN2 on a primary aliphatic carbon. So here it's got to look for some beta hydrogens, and we got the green beta hydrogens and the pink beta hydrogens. And so we've had this issue before a little bit, and we'll come back and look at that. But which hydrogen is going to get removed? Which alkene is going to be formed? This is Zaitsev's rule. So we have these two possible alkenes that could be formed. And what I want you to really do is notice that I'm really paying attention to the type of carbon, the pink and green and blues. Really look at the neighbors and the number of carbons attached to your alkenes. Because one of these has only one carbon attached to it, it is what we call less substituted. The other alkene, the one on the right, has two carbons attached to that alkene, and therefore we would call it more substituted. Okay? According to Zaitsev's rule, the more substituted alkene is going to always be your major product. So if you have a choice, you could go less substituted, more substituted, form the more substituted product as your major product, which means you kind of have to label both beta hydrogens and make sure you know where they could actually react and what could be formed. The reason for this is really the more substituted your carbons, your alkene is, the lower it is in energy. This looks like an energy platform here where we start with reactants, activation energies. More substituted alkenes are more stable. So they will stick around longer. And even though this is in equilibrium, the less substituted one, which is higher in energy, in equilibrium will go back to the reactants. And then when it comes over again, if it forms the more substituted one, it will stay. So it's not like you never form the less substituted one. It's just when you form that one, it goes back to reactants and then comes back, and sooner or later you make nothing but this bottom feeder, low energy major product. And where we've seen this before is a few video lectures ago, we started looking at eliminations of our cyclohexene. And in this slide, we just said you could make either one from the pink or blue hydrogens. And now Zaitsev to the rescue. Now I would hope that you would look at both of these alkene products and start labeling the alkene here is attached to 3 carbons, tertiary. The alkene here is attached to 2 carbons, that's a secondary. And so you can just kind of look and classify the type of alkene carbons, primary, secondary, tertiary, and notice this is the more substituted one. So this is the product I would hope that you would write as the major product and the only product if that's all I'm asking for. But sometimes we ask for major and minor, and this would be the minor product. You'd make a little bit of that. Okay, so Zaitsev to the rescue. Keep an eye on it. The major product is always the one with more alkyl groups on the carbons. And therefore, that's the goal when you're trying to form elimination products. And you have a choice. Okay, cool.
Sunny day, sweeping the clouds away. On my way to where the air is sweet. Can you tell me how to get to Sesame Street?
Yes, I love that song. That's just a feel-good song. That's why I have my feel-good shirt on today as well. See, it has little Volkswagen buses on it all over, VW buses, because it's kind of like, yeah, let's just go 60s feel-good Sesame Street song for kids on a topic that's totally sort of out of Zaitsev's rule and Hofmann's rule, but in chapter 11.12. It's called catalytic hydrogenation. And the reason I'm throwing it in here now as a little off-topic, cool reaction I'd like you to know is because we've been learning how to form alkenes. That's what chapter 9's all been about, how to make alkenes. I thought I'd show you one way you can destroy your alkene and get it back to an alkane if you want. It's kind of cool. You can go both ways. So this is hydrogen gas. And if you run hydrogen gas over either platinum or palladium catalyst, it never gets used up. The H2 molecule will actually add right on top of your double bond, and therefore add, as you can see, an syn addition here, if there's stereochemistry related to this. So it will add right on top, pushing the 2 groups to the other side, and you will create an alkane. So you can do this, and this H2 and platinum, this would do the same thing. If this was a triple bond, you would have just added, if it was, oh, bad news there. Sorry, hold on. Let's erase that. If it's a triple bond, then you would just be adding lots of hydrogens. You would be getting 2 H2s added to this triple bond and removing both pi bonds. So the only thing this H2 cannot react with and will not form and get rid of double bonds is in a benzene ring. So these two, no reaction. But all other kinds like this nitrile, this alkyne, these triple bonds, these pi bonds are easily chewed up by H2 and platinum and palladium. Okay? All right. So I just thought that was something you might want to see. And now let's get back to the show. Okay, the show is, how do you beat Zaitsev's rule and make, what if you wanted to make the less substituted alkene? Okay, yeah, right. That is a long name for a show. So, but that's probably why I'm not on TV. So let's see, how would you want to make the less substituted alkene? And the less substituted alkene is what's called a Hofmann elimination. Notice I put it in little letters. It's the fine print. It means that I'm rarely going to ever go, hey, show me Hofmann, show me Zaitsev. That these chemists are very well known for what they've done, and I appreciate it. But I'm not about to quiz you on whether you know the name of a dead chemist related to a certain reaction or not. What I want is for you to be able to travel through Orgoland and make the more substituted alkene, if that's what you want, or give you a way to make the less substituted alkene, if that's what you want. So here is one way you can beat Zaitsev's rule. If you have the possibility of creating a conjugated diene or a conjugated system, conjugation, if you recall, is when you have double single, double single, double single. These pi bonds are very resonance stabilized and they are very low in energy for this molecule. So if you have the ability to do that, in this one you do. Notice here is my leaving group. It is on a secondary carbon. I have a very nice tertiary, and sitting over here I only have a secondary. So according to Zaitsev's rule, I really should want to make the alkene over here. This is Zaitsev's product. Really substituted on that tertiary secondary carbon. But then notice the major product happens to be the less substituted one because of this pattern here. I can create a conjugated system if I just have the double bond form to the left of that leaving group and create a double single double bond. So this will always happen. Be on the lookout for maybe knee-jerk responses making the Zaitsev product. But if you have double bonds already on your molecule somewhere, or alkynes, or some kind of pi system, recognize this is going to want to make a bigger pi system, a bigger conjugated system, even if it's less substituted. Okay? Woo, that's a mouthful. All right, that's Hofmann's elimination. Is coming up. The other way, that is still Hofmann, because Hofmann is any way you can make the less substituted product, is using a big, huge, bulky base. Which one am I going to use? Which one's my favorite big, bulky base? Yes, T-butoxide rocks. Okay, there's my poster child for big, bulky base. And it's so big and bulky that it just can't find its way in on this tertiary carbon. This is too bulky, so it's very unhappy going there. So why fight it? What it will do is go the easy route and go way over here to this less substituted proton, this less substituted beta hydrogen, and pluck one of the green ones off and make the less substituted alkene, therefore beating Zaitsev's rule. So these are the two main ways to beat Zaitsev's rule. And so keep those in mind. I don't care which one you use. Sometimes you can't use the conjugated system because you don't have one. So really the bulky base is the way to go. Try these fun. Can you tell I'm having a fun day today? I'm wearing my VW bus shirt. It's a fun day today. Try these and please come to class with answers for these questions. One little word of warning or just notation issue. This sodium metal and this alcohol, even though they're both over the arrow, the sodium metal has no interest in reacting with the chlorinated compound. So this is going to do a reaction with this alcohol first, and then the product of that will react. So this will happen first, and then the product with that will go second. And tell me what products you make from that reaction. Oftentimes when we do these two-step syntheses, you can see we write it out as part 1 and part 2. That'd be really nice here, but sometimes they don't. And that's because sodium metal just has no interest in an alkyl chloride. So if they threw all these things in the pot, there's only one thing the sodium metal would want to play with. And that one you know from a previous commercial break that we had. Okay, go have fun with this. And here comes 17B right around the corner. Whew. Be on the lookout for it. I know I will. See you later, guys.